Hello everyone, welcome to my channel Chemistry is Fun. Today we will be dealing with a new topic, hybridization. Hybridization is the process in which there is mixing of atomic orbitals and needless to say all the atomic orbitals should be of nearly same energy, and the new orbitals which are formed, they are entirely new and they have equivalent energy. This method is called as hybridization. Now during hybridization, the atomic orbitals which take part, they are having similar energy and they should be of the same atom. Energy should be similar, atom should be same. For example, the s and p orbitals of carbon can hybridize. The total number of atomic orbitals which are participating in hybridization will decide the total number of hybridized atomic orbitals which are formed. For example, if one s and one p orbital, if they participate, then we will get two number of sp hybridized orbitals. So the number of orbitals is maintained. Hybridization takes place among orbitals, it doesn't take place among the electrons. After hybridization, we get the hybrid orbitals, and when they form the bonds, the bond formed is a sigma bond, as we can see in case of methane CH4. In methane, carbon atom undergoes sp3 hybridization. There are 4 number of sp3 hybridized atoms in carbon, as we can see. There are 4 sp3 hybridized atoms, orbitals in carbon atom. It's orbitals, hybridized orbitals. There are 4 number of sp3 hybridized orbitals in carbon atom, and each of the hybridized orbitals forms a sigma bond with the s orbital of hydrogen atom. So we have 4 number of sigma bonds between the sp3 hybridized orbitals of carbon and the s orbital of hydrogen. Now after the bond formation, if we find that the molecule will have a regular geometry if the hybrid orbitals after overlapping have shared pair of electrons. See, there are two possibilities. There may be shared pair of electrons, as we find in methane. All the electron pairs here we can see again. Here all the pairs are shared pairs because there has been a sharing of electrons between carbon and hydrogen. So if all are shared, the pair of electrons, they are shared pairs, then there will be a regular geometry. As we see in case of methane, the geometry is tetrahedral because the carbon atom is sp3 hybridized and all the electron pairs are shared electron pairs. But as in case of ammonia, there will be a lone pair of electrons on nitrogen atom. So the geometry will be distorted. Ammonia molecule is pyramidal in shape because there will be repulsion between the lone pair of electrons. As in case of ammonia, in nitrogen there is a lone pair. So there is a repulsion between the lone pairs and the bond pairs. The bond pairs are between nitrogen and hydrogen in ammonia. Because of this repulsion, the shape is distorted to a pyramidal shape. Now we just have a look at the type of hybridization and the resulting shape of the molecules. If the hybridization of the type sp, that is one s orbital and a p orbital participates in hybridization, we get a linear shape. If it is sp2 hybridization, then we have plain triangular shape. Here one s orbital and two p orbitals participate. If the hybridization is of the type sp3, we get tetrahedral shape. In case of dsp2, we have a square planar. If the hybridization is sp3d, the resultant shape will be trigonal bipyramid. sp3d2 results in octahedral shape. That is, you see, sp3d2 means total 6 hybridized orbitals will be resulting. In d3sp3, that is 3d orbitals, 1 s orbital and 3 p orbitals, total 7 hybrid orbitals we will be getting. The shape should be pentagonal bipyramidal. But again, In detail we will see afterwards. Depending upon whether the hybrid orbitals are occupied by shared pair of electrons or lone pair of electrons, the geometry may be regular or distorted. Now we also have to see some typical cases of hybridization. As we find in BeF2 molecule, there is sp hybridization in case of beryllium, and these hybridized orbitals, they overlap with the p orbitals of two fluorine atoms, resulting in BeF2 molecule. As we see here, say this is the beryllium. So in case of beryllium, there is sp hybridization. They will overlap with the p orbitals of two fluorine atoms. One beryllium atom, S and P, we will get two orbitals, two hybridized orbitals, and sp hybridization resulting in two orbitals. Each of these are similar, both are similar, so they can form overlapping bond formation, which are each a sigma bond again with fluorine. The bond angle is found to be 180 degrees. If we see methane molecule in detail, in general you see in the ground state of carbon there are two unpaired electrons in case of P, and there are two electrons in S. These 2s electrons are paired. You see in 2s there are paired electrons, 2p is unpaired. In the excited state, one electron from 2s is shifted to 2p. So now in order to gain tetravalency, all the four orbitals, that is 1 2s and 3 2p orbitals, all are singly occupied now. They are all unpaired. All these unpaired orbitals undergo hybridization, so we get 4 hybrid orbitals, and these will be sp3 hybridized orbitals. These 4 hybrid orbitals overlap with each orbital of 4 hydrogen atoms, and we get 4 sigma bonds. You see, these are all shared pairs here. All these bond forms between the sp3 hybridized orbitals of carbon and the s orbital of hydrogen. Since all are shared, these all are shared pairs, so there will be the normal tetrahedral shape. Here bond angle is 109 degree 28 minutes, which we usually find in sp3 hybridization case. Now in some cases, as we find mostly in the unsaturated compounds of carbon in organic chemistry, if there is a multiple bond, that is say double bond or triple bond, then there will be pi bonds also along with the sigma bonds. We will see two such examples. First is ethylene molecule. Ethylene molecule, it will be having sp2 hybridization. sp2 hybridized orbitals, that is 1s orbital and 2p orbitals combined to give 3 number of sp2 hybrid orbitals. This red color denotes the sp2 hybridized orbitals. These sp2 hybridized orbitals will form sigma bonds. One of the orbitals of each carbon overlap with the other sp2 hybridized orbital of the other carbon to form a sigma bond here, and the rest of the two sp2 hybridized orbitals form sigma bond with two hydrogen atoms. Same story for both the carbons. And the left out unhybridized orbital, that is the p orbital, which is denoted here by green color, that will overlap sideways overlap, leading to pi bond. This green color you can see, this is the unhybridized orbital. They overlap sidewise to form a pi bond. Here the bond angle is 120 degrees. So here two hybrid orbitals, one from each carbon atom, will form sigma bond with the other carbon, and the remaining ones sigma bond with hydrogen atoms. Unhybridized p orbitals, as I have shown with a green color in my diagram, will form pi bond by sidewise overlap. In case of acetylene molecule, there is sp hybridization of carbon. So one s orbital and one p orbital will hybridize to form two numbers of sp hybrid orbitals, and two unhybridized p orbitals will be left out for each carbon. The hybrid orbitals for each carbon will form a cc bond, which is a sigma bond, and ch bond, which is also a sigma bond. As we can see in this diagram, you see this is the sigma bond formation between the sp hybridized orbital of both the carbons, and here another sigma bond with the hydrogen atoms. The left out unhybridized p orbitals will have a sidewise overlap to form two pi bonds. So this is the case where we find multiple bonds, that is more than one bond. Here also in the ground state you see the carbon is having paired electron in s orbital, unpaired electron is in p orbital. There will be excitation of the electron, and then the 1s and 1p orbital undergoes sp hybridization. The two unhybridized orbitals are left out, they will participate for the pi bonding. So I hope you all could understand the topic which I explained today. Thanks for watching my video. Please subscribe to my channel. Thanks for watching. Thank you.